Picture the Earth from space, a blue marble suspended in the cosmic void. Zoom in through the clouds, past the sprawling cities and endless highways, down through layers of rock and sediment that tell the story of our planet's 4.5 billion year history. Now imagine rewinding time, watching continents drift apart, mountains rise and fall, oceans appear and vanish like puddles after rain. Watch as vast forests turn to coal, as shallow seas become limestone cliffs, as the very face of our world transforms again and again in an endless cycle of creation and destruction. This is the stage upon which we must ask one of the most provocative questions in science today. Could other civilizations have risen and fallen on Earth long before humans ever walked upright? Could we be not the first, but perhaps the second, third, or even 100th technological species to call this planet home? It sounds like science fiction, the stuff of late-night television shows and paperback novels. But it's a question that serious scientists are now beginning to explore with rigorous methodology and careful analysis. The human story, as we know it, spans roughly 6,000 years of written history. Our species, Homo sapiens, has existed for perhaps 300,000 years, a mere blink in geological terms. But Earth itself has been spinning through space for 4.54 billion years. That's a time span so vast it defies human comprehension. To put this in perspective, if Earth's entire history were compressed into a single 24-hour day, complex life would not appear until about 4 in the afternoon. The dinosaurs would rule for just over an hour before vanishing at 23 minutes to midnight. All of human history, from the first cave paintings to the International Space Station, would flash by in the final fraction of the last second. What happened during all those eons before we arrived? We know about the dinosaurs, of course, those magnificent reptiles that dominated terrestrial ecosystems for 165 million years. We know about the great extinctions, those catastrophic events that swept away entire branches of the tree of life. We know about the ice ages, the slow dance of evolution, the patient accumulation of atmospheric oxygen that made our own existence possible. But could there have been something else? Something we've missed entirely because we haven't known how to look for it? Consider what we do know about Earth's deep past. The Precambrian, that vast stretch of time before complex life appeared, encompasses nearly 90% of Earth's history. For most of that time, our planet was an alien world, with no oxygen in the atmosphere, no complex cells, no multicellular life. Yet even in those ancient eons, dramatic events were unfolding. Continents formed and broke apart. Massive volcanic eruptions reshaped the surface. Asteroid impacts larger than the one that killed the dinosaurs left their scars in the rock record. The question isn't entirely new. Ancient cultures around the world have told stories of lost civilizations, of golden ages that came before, of knowledge that was forgotten and had to be rediscovered. The Greeks spoke of Atlantis, that advanced island civilization that supposedly sank beneath the waves. Hindu texts describe cycles of creation and destruction spanning millions of years. Aboriginal Australian stories preserve memories of events that scientists now recognize as genuine geological phenomena from tens of thousands of years ago. But these were myths, legends, stories told around fires to explain the unexplainable. What's different now is that we have the scientific tools to investigate whether such possibilities could be real. We have radiometric dating to determine the age of rocks with precision. We have mass spectrometers that can detect trace chemicals in ancient sediments. We have deep drilling capabilities that can extract ice cores spanning hundreds of thousands of years, and rock cores that reach back millions of years into Earth's past. Most importantly, we now understand something that previous generations could not have imagined. We understand deep time. We understand that the Earth is not 6,000 years old, as many once believed, but billions of years old. We understand that the processes shaping our planet operate on timescales that dwarf human experience. We understand that what seems permanent and unchanging to us is actually dynamic and temporary when viewed from the perspective of geological time. This understanding changes everything about how we approach the question of prior civilizations. It's no longer a matter of looking for lost cities or ancient artifacts in the conventional archaeological sense. It's a matter of reading the chemical and physical signatures preserved in the Earth's rock record, searching for anomalies that might indicate technological activity in the distant past. In 2018, two researchers named Gavin Schmidt and Adam Frank published a paper that would reshape how we think about this question. Schmidt is a climate scientist at NASA's Goddard Institute for Space Studies, a world expert in understanding how human activities are changing Earth's climate. Frank is an astrophysicist at the University of Rochester who studies the evolution of planetary atmospheres and the search for life beyond Earth. They called their hypothesis the Silurian hypothesis, named after an ancient reptilian race from the British science fiction series Doctor Who. The name was somewhat tongue-in-cheek, but the science behind it was deadly serious. The hypothesis wasn't proposing that such civilizations actually existed, but rather asking a more fundamental question. If they had existed, would we be able to detect them? Their analysis was sobering. The geological record, they argued, is like a book with most of its pages missing, and many of the remaining pages are smudged, torn, or illegible. The processes that preserve evidence of past life are selective, rare, and easily disrupted. A technological civilization that lasted for thousands or even tens of thousands of years might leave barely a trace in the geological record, especially if it existed millions or tens of millions of years ago. The problem is not just one of preservation, but of recognition. How would we know an artificial structure or chemical signature if we saw it? How would we distinguish the traces of ancient technology from the countless natural processes that have shaped our planet? The challenge becomes even more daunting when we consider that any prior civilization might have used technologies completely different from our own, based on principles we haven't discovered or materials we haven't invented. Think about it this way. Take our current industrial civilization, with all its concrete and steel, its plastics and nuclear waste, its carbon emissions and chemical signatures. Now, imagine it disappeared tomorrow. How much evidence would remain after 1 million years? After 10 million years? After 100 million years? The answer is both humbling and terrifying. Almost nothing would survive in a recognizable form. Our cities would crumble, their concrete and steel no match for the patient work of wind, water, and chemical weathering. Our roads would crack and buckle as plant roots reclaim the surface. Our bridges would collapse, our skyscrapers would topple, our monuments would erode to nothing. Our metals would rust and corrode, returning to the oxides and sulfides from which we originally extracted them. Our plastics would break down under ultraviolet radiation and bacterial action, fragmenting into microscopic pieces that would eventually be incorporated into sedimentary layers. Even our most durable materials, the ceramics and glasses that we imagine might last forever, would eventually succumb to the relentless forces of geological recycling. Within a few 100,000 years, very little would remain on the surface. Within a few million years, even the subsurface traces would be difficult to detect. And within a few tens of millions of years, the evidence would be so fragmentary and ambiguous that future archaeologists might easily miss it entirely or mistake it for some natural phenomenon. This realization opens up a vast investigative frontier that spans multiple scientific disciplines. Geologists study the rock layers that preserve Earth's history, looking for chemical signatures that might indicate past industrial activity. They search for anomalous concentrations of metals, unusual isotopic ratios, or synthetic compounds that don't occur in nature. They examine the fine structure of sedimentary layers, looking for evidence of rapid environmental change that might indicate technological influence. Archaeologists examine the limits of their own field, trying to understand what kinds of evidence could survive across such immense timescales. They study the taphonomy of preservation, the complex processes that determine which organic and inorganic materials become fossilized and which disappear without a trace. They investigate how natural geological processes might mimic artificial structures, and how genuine artifacts might be altered beyond recognition by millions of years of physical and chemical change. Climatologists analyze ancient climate data, searching for unexplained warming or cooling events that might indicate technological influence. They examine ice cores, tree rings, and sediment cores for evidence of atmospheric composition, changes that can't be explained by known natural processes. They model how industrial emissions might appear in the paleoclimate record, and what signatures would distinguish artificial climate change from natural variability. Planetary scientists look at other worlds, trying to understand how planetary histories unfold and what traces advanced civilizations might leave behind. They study the atmospheres of Mars and Venus, searching for clues about how planetary environments evolve over geological time. They analyze data from exoplanets, looking for atmospheric signatures that might indicate industrial activity on distant worlds. They develop models of planetary evolution that can help us understand what to expect from our own planet's deep past. Each of these fields brings its own methods, its own limitations, and its own insights to bear on this extraordinary question. The investigation requires us to think like detectives, working a case where most of the evidence has been destroyed, where the witnesses are long dead, and where the crime scene has been altered beyond recognition by millions of years of natural processes. But science thrives on difficult questions, on mysteries that push the boundaries of what we think we know. The search for evidence of prior civilizations on Earth represents one of the most ambitious cold cases ever undertaken. It forces us to reconsider our place in the cosmic timeline, to question our assumptions about uniqueness and precedence, to imagine possibilities that stretch our understanding of life and intelligence in the universe. As we embark on this investigation, we must maintain the careful balance that defines good science. We must be open to extraordinary possibilities while remaining grounded in evidence and reason. We must distinguish between what we know, what we suspect, and what we merely hope might be true. We must be prepared to follow the evidence wherever it leads, even if it challenges our most fundamental assumptions about ourselves and our world. The stakes could not be higher. If we are truly alone in Earth's history, then we bear a unique responsibility as the planet's first and perhaps only technological species. But if others have come before us, then we join a cosmic conversation that spans deep time, and our choices today echo those made by civilizations lost to the ages. The Earth beneath our feet holds 4.5 billion years of secrets. Layer by layer, fossil by fossil, chemical signature by chemical signature, we're learning to read the story written in stone. And somewhere in that vast library of deep time, we may find that we are not alone and never have been. The question that won't go away is calling us to look deeper, to search more carefully, and to prepare ourselves for answers that might change everything we thought we knew about our world and our place within it. To understand why evidence of ancient civilizations might be so difficult to find, we must first grasp the true nature of geological time. The human mind struggles to comprehend timescales that stretch across millions and billions of years. We think in terms of lifetimes, generations, perhaps centuries at most. But the Earth operates on a completely different temporal scale, one where mountains rise and fall like waves, where entire species evolve and disappear, where the very geography of our planet transforms beyond recognition. Geologists have divided Earth's history into a hierarchical system of time units that helps us navigate this vast temporal landscape. The The largest divisions are called eons, stretching across hundreds of millions or billions of years. Earth's history encompasses 4 major eons: the Hadean eon, from 4.54 billion to 4 billion years ago, when our planet was still forming and cooling from its violent birth; the Archean eon, from 4 billion to 2.5 billion years ago, when the first primitive life forms appeared in ancient oceans; the Proterozoic eon, from 2.5 billion to 541 million years ago, during which complex cells evolved and the first multicellular organisms emerged; and finally, the Phanerozoic eon, from 541 million years ago to the present, the era of visible life that includes all the fossils we commonly recognize. Each eon is subdivided into eras, which are further divided into periods, then epochs, and finally ages. The Phanerozoic eon, for instance, includes the Paleozoic era, the age of ancient life, when fish first swam in the seas and plants colonized the land; the Mesozoic era, the age of reptiles when dinosaurs ruled the earth for over 160 million years; and the Cenozoic era, the age of mammals and flowering plants that continues today. But even these seemingly precise divisions blur when we consider the processes that preserve evidence across such vast timescales. The geological record is not like a library where each book is carefully catalogued and preserved on its proper shelf. It's more like a library that's been struck by earthquakes, floods, and fires countless times, where most of the books have been destroyed. Others have had their pages scattered by the wind, and the few remaining volumes are often damaged, incomplete, or illegible. The Earth's surface is in constant motion, driven by the immense forces of plate tectonics. Continents drift across the globe at rates of a few centimeters per year, colliding with each other to form mountain ranges, then splitting apart to create new ocean basins. The seafloor spreads along mid-ocean ridges, carrying oceanic crust away from these underwater mountain chains at the stately pace of human fingernail growth. But this seemingly gentle process has dramatic consequences over geological time. Every piece of oceanic crust older than about 200 million years has been recycled back into the Earth's mantle through the process of subduction. As oceanic plates collide with continental margins, the denser oceanic crust slides beneath the continents and disappears into the hot depths of the mantle, where it melts and eventually returns to the surface as volcanic rock. This means that roughly half of Earth's surface has been completely recycled since the time of the dinosaurs, erasing any traces of what might have existed there. Continental crust fares better, being less dense and more likely to remain at the surface. But even continents are constantly being reshaped by erosion, weathering, and tectonic forces. Mountain ranges that once towered as high as the Himalayas have been worn down to gentle hills over hundreds of millions of years. Rivers carve new valleys while filling others with sediment. Glaciers advance and retreat, scouring the landscape and depositing vast sheets of rock debris across entire regions. The net result is that the older we go in Earth's history, the less evidence we have preserved. Most of the rock record from the first half of Earth's history has been destroyed or so metamorphosed by heat and pressure that any original features are unrecognizable. Even from more recent times, the preservation is spotty and incomplete. Consider the process of sedimentary burial, one of the primary ways that evidence from the past becomes preserved in the geological record. When organisms die or artificial materials are discarded, they may become buried under layers of sediment deposited by rivers, lakes, or oceans. Over time, these sediment layers compact and cement together to form sedimentary rocks like sandstone, shale, and limestone. Occasionally, the buried materials may be preserved as fossils or chemical traces that can be detected millions of years later. But this process is far from guaranteed. Most organic material decomposes long before it can be buried deeply enough to avoid destruction. Even when burial does occur, the chemistry of the surrounding environment must be just right to prevent decay. Acidic conditions will dissolve bones and shells. Oxygen-rich environments will allow bacteria to consume organic matter before it can fossilize. The temperature and pressure during burial must remain within a narrow range that allows preservation without complete destruction. Artificial materials face similar challenges, but with additional complications. Many synthetic compounds are specifically designed to resist decay under normal environmental conditions, but even the most durable human-made materials can be broken down by the extreme conditions found deep within sedimentary basins. High temperatures can cause plastics to depolymerize into their constituent molecules. High pressures can cause metals to recrystallize, erasing any distinctive manufacturing signatures. Chemical interactions with groundwater can leach away trace elements or deposit new minerals that obscure original compositions. The rarity of fossilization becomes apparent when we consider how few organisms from the past are actually preserved as fossils. Paleontologists estimate that less than 1% of all species that have ever lived are represented in the fossil record. For individual organisms, the preservation rate is even lower, perhaps 1 in millions or tens of millions. The vast majority of life that has existed on Earth has vanished without leaving any direct trace of its existence. This preservation bias is not random. Hard parts like bones, shells, and teeth are much more likely to fossilize than soft tissues like skin, muscle, and organs. Organisms that live in environments where rapid burial is common, such as river deltas or shallow marine basins, are more likely to be preserved than those in upland terrestrial environments where erosion dominates. Species that exist in large numbers over wide geographic ranges have better odds of having at least some individuals preserved than rare, localized species. The same biases would apply to evidence of ancient civilizations. Durable materials like stone and ceramics would be more likely to survive than organic materials like wood and textiles. Structures built in lowland environments where sediment accumulation is rapid would have better preservation potential than those built on hilltops or mountain slopes where erosion is dominant. Widely distributed technologies would be more likely to leave detectable traces than localized innovations. But there's another layer of complexity that makes the search even more challenging. The geological record is not just incomplete, it's also been repeatedly disrupted and rearranged by subsequent geological processes. Layers of rock that formed in orderly sequence over millions of years can be folded, faulted, and overturned by tectonic forces. Erosion can remove entire sequences of strata, creating gaps in the record known as unconformities. Intrusive igneous rocks can cut through older layers, destroying evidence and resetting radiometric clocks. Metamorphism, the process by which existing rocks are transformed by heat and pressure, can completely alter the chemistry and structure of sedimentary layers. The gentle mudstone that might have preserved delicate traces of ancient activity can be converted into hard, crystalline schist, where no original features remain recognizable. Even the isotopic signatures that might indicate artificial processes can be reset by metamorphic temperatures, erasing crucial evidence. The net effect of all these processes is that our window into Earth's deep past becomes increasingly cloudy the further back we look. The Cenozoic era, covering the last 66 million years, is relatively well represented in the geological record. We have detailed knowledge of climate changes, evolutionary events, and even some catastrophic impacts during this time. The Mesozoic era, from 252 to 66 million years ago, is less complete but still reasonably well documented, at least for major geological and biological events. But as we go back further in time, the record becomes increasingly fragmentary. The Paleozoic era, from 541 to 252 million years ago, is known mainly from scattered outcrops and heavily metamorphosed rocks. The Precambrian, representing nearly 90% of Earth's history, is poorly understood despite decades of intensive study. This temporal degradation of the geological record has profound implications for the search for ancient civilizations. If a technological species had arisen during the well-documented Cenozoic era, we would have a reasonable chance of detecting its traces, assuming we knew what to look for. Evidence from the Mesozoic would be much more difficult to recognize, but might still be detectable under favorable circumstances. But a civilization that existed during the Paleozoic or earlier would face nearly insurmountable preservation challenges. The vast majority of rocks from these time periods have been so altered by subsequent geological processes that any original features are likely to be unrecognizable. The few unaltered sequences that do exist are small, scattered, and represent only tiny samples of what once existed. This doesn't mean that ancient civilizations are impossible to detect, but it does mean that we must be extremely clever about what we look for and where we look for it. We need to focus on signatures that are both distinctive enough to be recognized as artificial and durable enough to survive hundreds of millions of years of geological processing. We need to understand the limitations of our methods and be realistic about what kinds of evidence might actually be preserved. Most importantly, we need to appreciate that absence of evidence is not necessarily evidence of absence. The fact that we haven't found traces of ancient civilizations doesn't mean they never existed. It might simply mean that we haven't looked in the right places, or that we haven't developed the right techniques to recognize highly altered or degraded evidence. The Earth's deep time archive is vast, ancient, and largely unexplored. Every year, new analytical techniques allow us to extract more information from smaller and smaller samples of ancient rock. Every new discovery in geochemistry, paleontology, or planetary science provides fresh insights into how evidence might be preserved or destroyed over geological timescales. As we push deeper into Earth's history, we are learning to read fainter and fainter signals from an increasingly distant past. The story written in stone is difficult to decipher, but it's the only record we have of what happened during the 4 billion years before human beings appeared on the scene. Hidden somewhere in that vast library of rock and mineral may be the signatures of intelligence that predate our own, waiting for us to develop the wisdom and skill to recognize them. Archaeology, the scientific study of human history through material remains, has revealed extraordinary insights about our past. From the cave paintings at Lascaux to the pyramids of Egypt, from the buried cities of Pompeii to the terracotta warriors of China, archaeological discoveries have illuminated the rise and fall of civilizations across the globe. But archaeology has a fundamental limitation that becomes crucial when we consider the possibility of much more ancient civilizations. It depends entirely on the survival of physical evidence, and that evidence has very specific requirements for preservation. Walk through any major archaeological museum and you'll see the bias immediately. Display cases are filled with pottery shards, stone tools, metal artifacts, and jewelry. These are the materials that survive. What you don't see are the wooden houses where people actually lived, the textiles they wore, the leather goods they used daily, the organic foods they ate, or the countless perishable items that made up the bulk of their material culture. For every artifact on display, thousands of others have rotted away, leaving no trace of their existence. This preservation bias becomes more severe the further back in time we go. The oldest human artifacts we have are stone tools dating back nearly 3 million years. But these represent only a tiny fraction of what early humans must have made and used. They had to have created containers for carrying water, tools for processing plant foods, shelters for protection from the elements, and countless other items necessary for survival. Almost none of these have survived because they were made from materials that decay rapidly under normal environmental conditions. Even within the relatively recent historical period, our archaeological record is shockingly incomplete. Consider medieval Europe, a time and place that has been intensively studied by archaeologists for over a century. Despite thousands of excavations and millions of artifacts recovered, archaeologists estimate that we have physical evidence for less than 1% of all the settlements that once existed. The vast majority of medieval villages, farms, and even some towns have vanished completely, their locations forgotten, their remains ploughed under or built over by subsequent generations. This is what archaeologists call the 1% problem. For every site we know about and have studied, there are 99 others that we'll never find because no trace of them remains visible on the surface. These lost sites aren't necessarily less important than the ones we've discovered. They may have been home to innovations, technologies, or ways of life that we know nothing about because the evidence has been erased by time and human activity. The problem becomes even more acute when we consider how modern cities would appear to future archaeologists. Take Manhattan, one of the most intensively developed places on Earth. Millions of people live and work there, surrounded by countless artifacts of 21st century technology. But how much of this material culture would actually survive if the city were abandoned tomorrow? Let's run this thought experiment step by step. Imagine that all human activity on Manhattan ceases suddenly. The power grid shuts down, the maintenance stops, and nature begins to reclaim the island. What happens next? Within the first few years, the most fragile materials begin to disappear. Paper documents, photographs, and books are destroyed by moisture and insects. Fabrics rot away. Electronics fail as moisture penetrates their circuits and corrosion attacks their delicate components. Rubber and many plastics begin to break down under ultraviolet radiation from the sun. After a decade, vegetation starts to colonize the abandoned structures. Tree roots grow through cracks in concrete and asphalt, gradually breaking apart roads and sidewalks. Building facades begin to crumble as mortar deteriorates and steel reinforcements rust and expand. Windows break from thermal stress and falling debris. Interior spaces flood as drainage systems clog and roofing materials fail. A century later, most of the smaller structures have collapsed completely. Skyscrapers still stand, but they're heavily damaged and unsafe. The steel framework that seemed so permanent is now riddled with rust, weakened by decades of freeze-thaw cycles and chemical corrosion. Concrete has spalled and cracked as the steel reinforcement bars expanded through oxidation. Glass and aluminum facades have long since fallen to the streets below. After 1,000 years, even the largest buildings have mostly collapsed. The steel that once seemed indestructible has returned to iron oxide, rust that crumbles at the touch. Concrete has weathered back to its constituent sand and gravel. Only the most durable materials remain, foundations of quarried stone, perhaps some ceramic pipes and tiles, scattered fragments of the most chemically stable plastics. 10,000 years later, most traces of the great city have disappeared entirely. Successive cycles of vegetation growth, soil formation, and erosion have buried the few remaining fragments under layers of organic debris and sediment. Sea level changes and river meandering have reworked the shoreline. The bedrock geology remains, but the human signature has been almost entirely erased. This dramatic disappearance isn't speculation. We can observe similar processes in real time at abandoned settlements around the world. The ancient city of Angkor in Cambodia was abandoned in the 15th century and quickly overgrown by tropical forest. When French explorers rediscovered it in the 19th century, massive stone temples were barely visible beneath centuries of vegetation growth. Smaller wooden structures had vanished completely. In more temperate climates, the process is slower, but equally relentless. Ghost towns from the American Gold Rush era abandoned barely more than a century ago, are already largely reclaimed by nature. Only stone foundations and metal debris mark where busy communities once stood. In another few centuries, even these traces will be difficult to recognize. The implications for finding evidence of much older civilizations are sobering. If a technological society had existed 10 million years ago, or 50 million years ago, what traces would remain for us to discover? The answer depends critically on the materials they used and the geological processes that have operated since their disappearance. Stone structures have the best chance of survival, which is why megalithic monuments like Stonehenge and the Egyptian pyramids have endured for thousands of years. But even stone is not permanent. Limestone dissolves in acidic groundwater. Granite fractures through freeze-thaw cycles and chemical weathering. Sandstone erodes grain by grain in wind and rain. Over millions of years, even the most massive stone structures would be reduced to scattered rubble and eventually to nothing at all. Metals present a different challenge. In their pure form, most metals are thermodynamically unstable at Earth's surface and will gradually oxidize back to their natural ore minerals. Iron becomes rust, copper becomes malachite and azurite. Even gold, the most chemically stable metal, can be dissolved and transported by certain natural chemical processes over geological time. But metals do have one advantage over stone. They can leave geochemical signatures in sediments long after the original objects have disappeared. Unusual concentrations of copper, tin, or other industrial metals in ancient sedimentary layers might indicate past technological activity, even if no actual artifacts remain. These chemical fingerprints are often more durable than the materials themselves. Ceramics and fired clay represent another category of potentially durable materials. Once fired at high temperatures, clay becomes chemically stable and resistant to weathering. Pottery shards are among the most common archaeological finds precisely because they survive so well in most environments. But ceramics also have limitations. They're brittle and easily broken into small fragments that become harder to recognize as artificial. Over millions of years, even ceramic fragments would be worn down to clay-sized particles and dispersed beyond recognition. The newest materials in human technology present the most uncertainty. Plastics are chemically complex and vary enormously in their stability. Some break down rapidly under environmental conditions, while others appear to be nearly indestructible. But we simply don't know how plastics will behave over geological timescales because they haven't existed long enough for us to observe their long-term fate. Early studies suggest that some plastic polymers might survive for thousands or even tens of thousands of years in favorable environments. But hundreds of millions of years? The chemical bonds that give plastics their unique properties would likely be broken by the heat, pressure, and chemical reactions encountered during deep burial and geological processing. Nuclear materials present perhaps the most interesting case for long-term preservation. The radioactive isotopes produced by nuclear reactors and weapons have decay rates that are completely independent of environmental conditions. Plutonium-239 has a half-life of 24,000 years. Some nuclear waste will remain radioactive for hundreds of thousands of years. These isotopic signatures would be detectable in ancient rocks long after any physical artifacts had disappeared. But here we encounter another limitation of the archaeological approach. Traditional archaeology focuses on finding and excavating intact sites where artifacts remain in their original context. The techniques and methods of archaeology are designed for working with objects and structures that are still recognizable as human-made, even if they're damaged or incomplete. Detecting the subtle geochemical signatures of ancient technology requires a completely different approach. Instead of excavating buildings and analyzing pottery shards, we need to collect sediment samples and analyze them with mass spectrometers. Instead of mapping the layout of ancient cities, we need to look for anomalous chemical compositions in rock layers. Instead of studying the style and function of artifacts, we need to search for isotopic ratios that don't match natural processes. This shift from conventional archaeology to geochemical detective work represents a fundamental change in how we approach the search for ancient intelligence. It requires collaboration between archaeologists, geologists, geochemists, and planetary scientists. It demands new analytical techniques and new ways of thinking about what constitutes evidence of past technological activity. The archaeological blind spot isn't a failure of the discipline, but rather a recognition of its natural limitations. Archaeology has been extraordinarily successful at reconstructing human history over the last few thousand years, and it continues to provide crucial insights into how our ancestors lived and developed. But when we're looking for evidence of civilizations that might have existed millions or tens of millions of years ago, we need to acknowledge that conventional archaeological methods are simply not adequate to the task. This doesn't mean the search is hopeless. It means we need to be more creative about what we look for and where we look for it. We need to think like forensic scientists working a cold case where the crime scene has been contaminated and most of the physical evidence has been destroyed. We need to look for subtle clues, chemical fingerprints, and statistical anomalies that might indicate artificial processes in the distant past. The 1% problem that affects historical archaeology becomes even more severe when applied to prehistoric civilizations. If we can only find evidence for 1% of medieval settlements, how much evidence might we expect to find for civilizations that existed 1,000 times longer ago? The mathematics are daunting, but not necessarily discouraging. Science has repeatedly shown that even tiny amounts of evidence can provide profound insights when analyzed with sufficiently sophisticated techniques. A few grams of moon rock told us about the formation of the solar system. Trace amounts of iridium in sedimentary rocks revealed the asteroid impact that killed the dinosaurs. The faint chemical signatures of ancient atmospheres, preserved in ice cores, have revolutionized our understanding of past climate change. Perhaps the traces of ancient intelligence are out there, waiting in rock layers we haven't yet learned to read properly. Perhaps the blind spot isn't permanent, but simply a limitation of our current techniques and understanding. As our analytical capabilities continue to improve, we may find that the Earth has been keeping secrets that are finally ready to be revealed. In the shadowy world between legitimate science and fringe speculation lies a category of objects and phenomena known as OOPArts, short for out-of-place artifacts. These are items that supposedly don't belong in the geological or archaeological context where they were found. Objects that seem to challenge our understanding of when certain technologies were developed or when human civilization first emerged. From ancient batteries in Baghdad to allegedly modern fossils in coal seams, OOPArts have captured the imagination of amateur researchers and conspiracy theorists for decades. But the scientific reality of OOPArts is far more mundane than their dramatic reputation suggests. The vast majority of these anomalous objects turn out to be misidentified natural formations, modern contamination of older deposits, hoaxes, or simply misunderstood artifacts from known historical periods. The process of investigating these claims provides valuable lessons about how to distinguish genuine anomalies from false positives, skills that become crucial when searching for evidence of truly ancient civilizations. Consider the famous case of the Baghdad Battery, a small clay jar discovered in 1936 near Baghdad, Iraq. The jar contained a copper cylinder and an iron rod, leading some researchers to speculate that it might have been an ancient galvanic cell capable of producing electric current. The artifact was dated to around 250 BCE, which would make it the oldest known battery by over a millennium. The battery interpretation gained popular attention and has been featured in countless books and television shows about ancient mysteries. But careful scientific analysis tells a different story. The copper cylinder shows no signs of electrolytic corrosion that would be expected if it had actually been used to generate electricity. Similar jars from the same period and region were commonly used for storing sacred scrolls, and the copper and iron components were likely just scroll handles that had been inserted into the jar for safekeeping. More importantly, there's no evidence that the ancient Mesopotamians had any use for electricity or any technology that would have required an electrical power source. The jar exists in complete isolation, with no associated artifacts or technologies that would make sense in the context of electrical experimentation. It's a classic example of imposing modern interpretations on ancient objects without considering their actual historical and cultural context. The Antikythera mechanism represents the opposite end of the spectrum. This complex bronze device, recovered from a Roman shipwreck dating to around 65 BCE, initially seemed impossible for its time period. Early examinations revealed a sophisticated system of gears that appeared far too advanced for ancient technology. Some researchers suggested it might be evidence of anachronistic knowledge or even extraterrestrial influence. But patient scientific investigation revealed the truth to be far more remarkable than any conspiracy theory. The device turned out to be an analog computer designed to predict the positions of celestial bodies, calculate the timing of eclipses, and track the 4-year cycle of Olympic Games. It represented the pinnacle of Hellenistic mechanical engineering, incorporating mathematical and astronomical knowledge that we know the Greeks possessed. The Antikythera mechanism teaches us an important lesson about anomalies. Sometimes objects really are out of place in terms of our expectations, but for reasons that ultimately make perfect sense within their historical context. The mechanism seemed impossible only because we had underestimated the technological capabilities of ancient Greek craftsmen, not because it represented impossible knowledge or anachronistic technology. This principle becomes crucial when evaluating claims about much older anomalies. The Klerksdorp spheres, small metallic objects found in Precambrian rock formations in South Africa, have been cited as evidence of artificial manufacturing processes dating back billions of years. The spheres are nearly perfectly round and appear to have parallel grooves around their circumference, features that some researchers argue could not have been produced by natural processes. But detailed mineralogical analysis reveals a much more prosaic explanation. The spheres are composed of pyrophyllite, a soft metamorphic mineral that commonly forms spherical concretions through natural geological processes. The parallel grooves result from the way the mineral crystallizes during metamorphism, creating natural fracture patterns that can appear remarkably regular to the untrained eye. Similar natural processes can create objects that look startlingly artificial. Concretions, nodules of mineral matter that form within sedimentary rocks, can take on almost any shape depending on the chemical and physical conditions during their formation. Some concretions are perfectly spherical, others are cylindrical or disc-shaped. Some have internal structures that look like gears, screws, or electronic components when viewed in cross-section. The key to distinguishing natural from artificial objects lies in understanding the formation processes and conducting appropriate analytical tests. Natural concretions, no matter how artificial they may appear, will always show mineralogical and chemical signatures consistent with known geological processes. Artificial objects, by contrast, should show evidence of manufacturing techniques, material compositions, or structural features that cannot be explained by natural formation. But this analytical approach requires sophisticated equipment and expertise that are not always available to amateur researchers who make initial discoveries. Many OOPART claims originate from well-meaning individuals who find unusual objects but lack the scientific background to properly evaluate what they've discovered. The objects then enter a cycle of sensationalized promotion through non-peer-reviewed publications and internet forums where speculation and wishful thinking can quickly overwhelm factual analysis. The Ica stones provide a perfect example of how this process can spiral out of control. These carved stones, allegedly discovered in Peru and depicting humans interacting with dinosaurs and using advanced technology, were promoted as evidence of ancient advanced civilizations. The stones showed detailed engravings of surgical procedures, astronomical observations, and even what appeared to be spacecraft and helicopters. The stones seem to challenge everything we know about both human history and the extinction of dinosaurs. But scientific investigation quickly revealed them to be modern forgeries. The carving marks were fresh, showing none of the weathering that would be expected from genuinely ancient artifacts. The artistic style was inconsistent with known pre-Columbian art traditions. Most tellingly, the stone surfaces showed traces of modern tools and abrasives used in their manufacture. The Ica stones case also illustrates another common problem with U parts, the issue of provenance. Genuine archaeological artifacts are always found in specific geological and cultural contexts that can be documented and verified. The stones had no reliable provenance, appearing instead through a network of local dealers who claimed to have found them in caves but could never lead researchers to the actual discovery sites. This lack of proper archaeological context is a red flag that appears repeatedly in OOP art claims. Genuine scientific discoveries are documented from the moment of discovery, with careful records of exactly where objects were found, what geological layers they came from, and what other materials were associated with them. This contextual information is often more important than the objects themselves in determining their age and significance. The peer review process provides another crucial filter for separating genuine anomalies from false claims. When legitimate researchers discover something unusual, they publish their findings in scientific journals, where other experts can examine the evidence and methodology. This process, while sometimes slow and conservative, has proven remarkably effective at identifying errors, detecting fraud, and ensuring that only well-supported claims become accepted scientific knowledge. U-part promoters typically bypass this peer review process entirely, publishing their claims in popular books, magazines, or websites where there is no systematic fact-checking or expert evaluation. They often argue that the scientific establishment is closed-minded or conspiratorial, but the reality is that scientists are generally eager to investigate genuine anomalies. Revolutionary discoveries that overturn accepted knowledge bring fame and career advancement to their discoverers. The few cases where OOP art claims have been submitted for peer review have not fared well. The analytical methods turn out to be inadequate, the interpretations prove to be unjustified, or the objects themselves turn out to be misidentified natural phenomena or modern forgeries. This consistent pattern of failure under scientific scrutiny is itself significant evidence against the extraordinary claims made for these objects. But this doesn't mean we should dismiss all unusual discoveries out of hand. Science has a long history of genuine surprises that initially seemed impossible or anachronistic. The discovery of deep-sea hydrothermal vents revealed entire ecosystems living without sunlight in conditions previously thought to be uninhabitable. The identification of impact craters on Earth overturned the prevailing belief that our planet had been geologically quiet compared to other worlds in the solar system. The key is to maintain a balance between skepticism and openness, to be willing to consider extraordinary claims while demanding extraordinary evidence. This means applying rigorous analytical methods, documenting discovery contexts carefully, and subjecting findings to peer review. It means being willing to admit when we're wrong, but also being cautious about accepting claims that would require us to rewrite fundamental aspects of our understanding of history and geology. This balanced approach becomes especially important when we consider the possibility of finding genuine evidence of ancient civilizations. Such evidence would necessarily appear anomalous at first, challenging our assumptions about when technological development occurred on Earth. but it would also need to meet the same standards of scientific rigor that we apply to any extraordinary claim. Genuine evidence of ancient technology should show consistent patterns across multiple discovery sites, not isolated anomalies that appear only once. It should be associated with other artifacts or environmental changes that make sense in the context of a technological civilization. It should survive scientific scrutiny and peer review, with multiple independent laboratories confirming unusual compositions or structures. Most importantly, genuine ancient technology should show evidence of technological progression and development, not just isolated advanced artifacts appearing without context. Real civilizations develop their technologies gradually, building on previous innovations and leaving traces of experimental and developmental phases. A genuine ancient technological civilization should leave evidence of this progression, not just a few impossibly advanced objects scattered randomly through the geological record. The search for such evidence requires us to be simultaneously more sophisticated and more skeptical than typical OOP-ART investigations. We need better analytical techniques, more careful documentation, and more rigorous peer review. We need to understand how natural processes can mimic artificial structures, how contamination can create false signatures, and how human psychology can lead us to see patterns that don't actually exist. But we also need to remain open to the possibility that genuine anomalies might exist, waiting to be discovered by researchers with the right combination of scientific skill and intellectual courage. The Earth has surprised us before with discoveries that seemed impossible until they were confirmed by careful investigation. It may surprise us again, but only if we approach the search with a rigorous methodology that separates real science from wishful thinking. The lessons learned from investigating OOPArts provide a valuable foundation for the much more challenging task of searching for evidence of truly ancient civilizations. They teach us about the importance of context, the power of peer review, and the need to distinguish between what seems anomalous and what actually is anomalous. Most importantly, they remind us that extraordinary claims require extraordinary evidence, and that the extraordinary nature of a claim is no excuse for abandoning the methodological rigor that makes science reliable. Nature is the ultimate architect, sculptor, and engineer. Over billions of years, geological processes have created structures so precise, so geometric, so seemingly artificial, that they can fool even experienced scientists into thinking they're looking at the work of intelligence, rather than the patient artistry of physics and chemistry. Understanding how nature creates these imposters is crucial for anyone hoping to identify genuine traces of ancient technology, because the false positive problem represents one of the greatest challenges in the search for evidence of prior civilizations. Standing on the coast of Northern Ireland, looking out at the Giant's Causeway, it's easy to understand why early visitors thought they were seeing the remains of an ancient road or causeway built by giants or some advanced civilization. Thousands of hexagonal stone columns rise from the sea like perfectly engineered stepping stones, their geometric precision so exact that they appear to have been cut and fitted by master stonemasons. The columns are so regular, so obviously geometric, that the artificial interpretation seems almost inescapable. But the Giant's Causeway is entirely natural, formed by the cooling and contraction of basaltic lava flows approximately 50 million years ago. As the molten rock cooled, it contracted uniformly, creating a regular pattern of tensional stress that fractured the solidifying basalt into hexagonal columns. The process is governed by the same physical principles that cause mud to crack into polygonal patterns when it dries, but operating on a much larger scale and over much longer time periods. The hexagonal shape isn't arbitrary or coincidental. It represents the most efficient way for cooling rock to relieve uniform tensional stress, minimizing the total length of fractures needed to accommodate the volume change. Nature consistently produces hexagonal patterns when uniform stress is applied to homogeneous materials, from the cells in a honeycomb to the convection cells in a pot of boiling water. Similar columnar jointing can be found in volcanic regions around the world, creating structures that consistently inspire artificial interpretations. The Devil's Tower in Wyoming rises like a massive stone skyscraper from the surrounding plains, its fluted columns so regular that Native American legends describe it as the result of supernatural intervention. The Devil's Postpile in California displays columnar jointing so perfect that early geologists struggled to accept its natural origin. But columnar basalt represents just one category of nature's deceptive creations. Crystal growth can produce structures that appear even more artificial than volcanic columns. The mineral pyrite, commonly known as fool's gold, naturally forms perfect cubes with mirror-flat faces and razor-sharp edges. These crystals can grow to enormous sizes, creating geometric forms that look like they were machined rather than grown. Fluorite crystals take the illusion even further, forming perfect octahedra that appear to have been cut by a lapidary. Some fluorite specimens display internal structures that look like electronic circuits or mechanical components, with regular arrays of geometric voids and inclusions that seem too organized to be natural. Yet every one of these features results from the orderly arrangement of atoms in the crystal lattice, following the immutable laws of chemistry and physics. Perhaps even more deceptive are the structures created by sedimentary processes. Concretions, those spherical or cylindrical masses of mineral matter that form within sedimentary rocks, can take on shapes that are virtually indistinguishable from manufactured objects. Some concretions are perfectly spherical. Others form cylinders with flat ends that look like industrial pipes or containers. The famous Meraki boulders of New Zealand are concretions so perfectly spherical that they appear to have been manufactured to precise specifications. Even more remarkable are septarian concretions, which develop internal patterns that can look like gears, circuit boards, or other technological devices when cut open. These patterns form as the concretions crack during drying, and the cracks are filled with different minerals, creating geometric networks that can appear startlingly artificial. The regularity of these patterns results from the physics of stress distribution and crack propagation, processes that naturally tend to produce geometric forms. Erosional processes can be equally deceptive. The action of wind and water can carve rock into shapes that appear to have been sculpted by intelligent hands. Natural arches, balanced rocks, and carved canyons can display such perfect proportions and smooth surfaces that they seem artificial. The wave formation in Arizona looks like it was shaped by a giant's hands, its flowing curves and smooth surfaces defying the common image of rough, chaotic natural erosion. Even more challenging are the structures created by biological processes that can persist long after the organisms that created them have vanished. Stromatolites, layered structures created by ancient bacterial mats, can form remarkably regular patterns that might be mistaken for artificial construction. Some stromatolites display concentric rings, parallel layers, or branching patterns that appear too organized to be biological. Trace fossils present another category of potential false positives. Burrows created by ancient animals can form networks that look like artificial tunnels or drainage systems. Some trace fossils create patterns that appear to show tool marks, construction activities, or even primitive writing systems. The famous Ediacaran trace fossils include structures that early researchers interpreted as everything from primitive roads to landing strips for ancient aircraft. The problem becomes even more complex when we consider how these natural structures can be modified by subsequent geological processes. Tectonic forces can fold and fracture natural formations, creating new geometric patterns that enhance their artificial appearance. Weathering can smooth rough surfaces and enhance linear features, making natural structures appear more refined and purposeful. Chemical alteration can change the composition and appearance of natural structures, sometimes creating materials that don't match the surrounding geology and appear to be foreign or artificial. Hydrothermal processes can deposit unusual minerals in regular patterns, creating chemical signatures that might be mistaken for industrial contamination or technological residues. The challenge for researchers is developing reliable methods to distinguish between natural and artificial structures, especially when the structures in question are ancient, weathered, and potentially altered by millions of years of geological processes. This requires understanding not just what artificial structures should look like, but also the full range of what natural processes can produce. Geologists have developed sophisticated techniques for making these distinctions. Crystallographic analysis can determine whether mineral structures formed through natural crystal growth or artificial processing. Geochemical analysis can identify trace elements and isotopic signatures that indicate natural versus artificial formation processes. Structural analysis can determine whether geometric patterns result from known physical processes or require artificial intervention. But these techniques require careful application and expert interpretation. The same analytical methods that can definitively identify artificial materials in modern contexts become much more challenging to apply to ancient, weathered, and potentially contaminated samples. The signatures of artificial processing may be obscured or completely erased by subsequent geological processes. Consider the famous Bimini Road, a linear arrangement of rectangular stone blocks on the ocean floor near the Bahamas. When it was first discovered in 1968, some researchers interpreted it as evidence of an ancient constructed causeway, possibly related to the lost civilization of Atlantis. The blocks appeared to be too regular and well arranged to be natural formations. But detailed geological investigation revealed a much more mundane explanation. The Bimini Road is composed of beach rock, a natural sedimentary formation that commonly develops in shallow marine environments. As layers of beach sediment become cemented by calcium carbonate, they form flat-lying slabs that can fracture along regular joint patterns. When sea level rises or the seafloor subsides, these fractured slabs can be exposed on the ocean floor, creating linear arrangements of rectangular blocks that appear artificial but are entirely natural. The Bimini Road case illustrates how important it is to understand local geological processes when evaluating potentially artificial structures. What appears anomalous in one geological context may be perfectly normal in another. Beach rock formation is well understood and commonly observed in tropical marine environments, but researchers unfamiliar with these processes might easily mistake the resulting structures for artificial construction. This principle becomes crucial when searching for evidence of ancient civilizations. Any potentially artificial structure must be evaluated in the context of the geological processes that could have operated in that location over the relevant time period. Structures that appear anomalous based on our everyday experience with human construction might be perfectly normal products of local geological conditions. The false positive problem is compounded by the human tendency to see patterns and purpose in random or natural phenomena. Our brains are evolutionarily programmed to recognize artificial structures and potential threats, leading us to perceive organization and intentionality, even in purely random arrangements. This psychological bias, known as pareidolia, can cause us to interpret natural formations as artificial constructions, even when there's no objective basis for such interpretations. Statistical analysis provides one tool for overcoming this bias. Natural processes, while they can create remarkably regular structures, typically show characteristic patterns of variation and irregularity that can be quantified and compared to the signatures of artificial construction. Genuine artificial structures should show evidence of planning, standardization, and purposeful design that goes beyond what natural processes typically produce. But statistical analysis has its own limitations, especially when applied to small samples or highly weathered specimens. The statistical signatures of artificial construction may be obscured by subsequent modification, or the sample size may be too small to reliably distinguish natural from artificial patterns. In some cases, natural processes can produce structures that are more regular and geometric than anything humans typically construct. The solution to the false positive problem requires a multidisciplinary approach that combines geological expertise, analytical chemistry, materials science, and statistical analysis. No single line of evidence is sufficient to definitively identify artificial structures in ancient geological contexts. Instead, researchers must build cumulative cases based on multiple independent lines of evidence that all point toward the same conclusion. This approach has been successfully applied to identifying genuine traces of early life in ancient rocks, a problem that shares many similarities with the search for ancient technology. Distinguishing biological from non-biological structures in rocks that are billions of years old requires the same careful attention to natural processes, the same sophisticated analytical techniques, and the same rigorous standards of evidence that would be needed to identify ancient technological traces. The techniques developed for astrobiology research provide valuable models for approaching the search for ancient civilizations. Astrobiologists have learned to be extremely cautious about claiming to have found evidence of life in ancient rocks or meteorites, because the stakes are so high and the potential for false positives is so great. The same caution and methodological rigor would be essential for any credible search for evidence of prior technological civilizations. Understanding nature's ability to create apparently artificial structures doesn't diminish the possibility that genuine artificial structures might exist in ancient rocks. Instead, it provides the foundation for developing reliable methods to distinguish the real from the apparent, the artificial from the natural. Only by understanding what nature can create can we hope to recognize what nature could not have created. The false positive problem represents a significant challenge, but not an insurmountable one. Science has repeatedly demonstrated its ability to distinguish between competing explanations for natural phenomena, even when the distinctions are subtle and the evidence is limited. The same methodological approaches that have allowed us to understand the formation of the Giant's Causeway, identify the biological origin of stromatolites, and explain the geometry of crystal structures can be applied to the search for genuine traces of ancient intelligence. The key is maintaining the same standards of evidence and the same commitment to rigorous methodology that characterizes successful scientific investigation in any field. Nature may be a master of deception, but science has proven to be an even more capable detective. The history of life on Earth is punctuated by moments of almost unimaginable destruction, events so catastrophic that they reset the biological clock and forced evolution to begin again from whatever survivors managed to endure the chaos. These mass extinction events represent nature's ultimate reset button, wiping out entire ecosystems and erasing millions of years of evolutionary progress in geological instants. Understanding these catastrophes and their causes provides crucial insight into how evidence of ancient civilizations might have been destroyed, and why the search for such evidence faces such formidable challenges. 5 major mass extinction events stand out in the fossil record like scars on the face of deep time. Each represents a moment when the normal rules of survival were suspended, when being perfectly adapted to existing conditions became a liability rather than an advantage, when random chance rather than natural selection determined which lineages would survive to populate the post-apocalyptic world. The most recent and famous of these events occurred 66 million years ago at the boundary between the Cretaceous and Paleogene periods. This is the extinction that ended the age of dinosaurs, wiping out not just the giant reptiles that had dominated terrestrial ecosystems for over 160 million years, but also countless other species of plants, marine organisms, and smaller animals. The cause of this extinction is now well established. a massive asteroid impact that struck the Yucatan Peninsula with the force of billions of nuclear weapons. The Chicxulub impactor, as it's now known, was probably about 10 kilometers in diameter, traveling at a velocity of 20 kilometers per second when it slammed into Earth's surface. The initial impact created a crater over 150 kilometers across and triggered a cascade of catastrophic effects that transformed the entire planet within hours and days. The immediate effects were apocalyptic. The impact vaporized the asteroid and massive amounts of crustal rock, launching billions of tons of debris into the atmosphere and beyond. Much of this material fell back to Earth as superheated glass spherules that turned the sky into a rain of molten rock, igniting wildfires across entire continents. The thermal pulse from these falling spherules was so intense that any large animal caught in the open would have been literally cooked alive. But the immediate effects were just the beginning. The impact threw so much dust and ash into the atmosphere that sunlight was blocked for months, or possibly years, creating a global winter that shut down photosynthesis and collapsed food chains from the bottom up. Acid rain, generated by sulfur compounds, blasted from evaporate deposits at the impact site, poisoned lakes and rivers. Massive earthquakes and tsunamis devastated coastlines around the world. The Chicxulub impact demonstrates how quickly and thoroughly a single catastrophic event can reshape the entire planet. Within a matter of days or weeks, ecosystems that had remained stable for millions of years were completely destroyed. Species that had successfully survived countless environmental challenges were suddenly extinct. The biological diversity that had accumulated over tens of millions of years was erased in what amounts to an instant in geological time. But devastating as it was, the end Cretaceous extinction was not the worst catastrophe in Earth's history. That distinction belongs to the end Permian extinction, which occurred approximately 252 million years ago and represents the closest life on Earth has ever come to complete annihilation. This event, sometimes called the Great Dying, eliminated an estimated 96% of marine species and 70% of terrestrial vertebrate species. It was so severe that it took millions of years for biodiversity to recover to pre-extinction levels. The cause of the end Permian extinction was different from the asteroid impact that ended the Cretaceous. Instead of extraterrestrial bombardment, the killing mechanism appears to have been massive volcanism on a scale that dwarfs anything in recorded human history. The Siberian Traps, a vast region of volcanic rock covering over 2 million square kilometers, erupted continuously for hundreds of thousands of years, the pouring of enormous volumes of lava, ash, and toxic gases into the atmosphere and oceans. The environmental effects of this prolonged volcanic catastrophe were devastating and complex. Carbon dioxide released by the eruptions triggered severe global warming. Sulfur compounds created acid rain that acidified the oceans and poisoned terrestrial environments. Toxic metals like mercury and lead accumulated to lethal levels in ecosystems worldwide. Oxygen levels in the atmosphere and oceans plummeted as organic matter was oxidized by volcanic emissions. Perhaps most devastating of all, the warming oceans released massive amounts of methane hydrates from seafloor deposits, creating a runaway greenhouse effect that pushed global temperatures to levels that were lethal for most forms of life. The oceans became stratified and oxygen depleted, creating vast dead zones where nothing could survive. On land, the combination of extreme heat, toxic air, and acid rain created conditions that approach the limits of what life can endure. The end Permian extinction illustrates how prolonged environmental stress can be even more destructive than sudden catastrophic impacts. While the Chicxulub asteroid killed through shock and immediate environmental disruption, the Siberian Traps volcanism killed through sustained poisoning and gradual degradation of life support systems. Both mechanisms were equally effective at erasing the biological record of millions of years of evolution. These mass extinction events raise profound questions about the vulnerability of technological civilizations to similar catastrophes. Modern human civilization depends on complex global networks of trade, communication, and resource distribution that could be easily disrupted by the kind of environmental changes that accompanied past extinction events. Our technological infrastructure is concentrated in coastal areas that would be devastated by the tsunamis generated by major asteroid impacts. Our agriculture depends on stable climate conditions that would be impossible to maintain during prolonged volcanic winters or runaway greenhouse warming. But the implications go beyond the immediate survival of technological species. Mass extinction events also have the power to erase virtually all traces of complex civilizations from the geological record. The environmental conditions that accompany these catastrophes are precisely those that are most destructive to the kinds of materials and structures that technological species are likely to produce. Consider what would happen to modern human civilization if it were subjected to the environmental conditions that accompanied the end Permian extinction. The combination of extreme heat, acid rain, and toxic atmospheric chemistry would rapidly destroy most organic materials and corrode most metals. The massive volcanism would bury surface structures under thick layers of lava and ash. The ocean acidification would dissolve shells, bones, and any calcium carbonate-based materials. Even more importantly, the social and economic disruption caused by such environmental catastrophes would likely prevent any systematic effort to preserve records or artifacts for future discovery. Technological civilizations facing imminent extinction would be focused on immediate survival, not on leaving messages for hypothetical future intelligence. Libraries would be abandoned, data storage systems would fail, and the accumulated knowledge of entire civilizations would be lost, along with the civilizations themselves. The concept of the Great Filter, developed by economist Robin Hanson, provides a framework for understanding how catastrophic events might prevent the development or persistence of technological civilizations. The Great Filter hypothesis suggests that there must be some evolutionary step or challenge that is extremely difficult to overcome, explaining why we don't observe evidence of technological civilizations elsewhere in the universe despite the vast number of potentially habitable planets. Mass extinction events could represent one type of Great Filter, randomly eliminating technological species before they have time to develop the capabilities needed to survive planetary-scale catastrophes. A civilization that develops technology during a geologically quiet period might thrive for thousands or even hundreds of thousands of years, only to be wiped out by an asteroid impact or supervolcanic eruption that occurs without warning. The timing of such events would be crucial for determining what traces might survive in the geological record. A civilization that was eliminated early in its technological development might leave little more evidence than stone tools and simple metal artifacts. A more advanced civilization might leave more durable traces, but even these could be completely erased by the environmental conditions that accompany mass extinction events. The frequency of major catastrophic events suggests that technological civilizations would have relatively narrow windows of opportunity to develop protective capabilities. Major asteroid impacts capable of causing global environmental disruption occur roughly every 50 to 100 million years. Supervolcanic eruptions large enough to trigger mass extinctions happen on similar timescales. Ice ages, while less immediately catastrophic, occur every few 100,000 years and could severely stress technological civilizations that lack adequate preparation. These timescales are long compared to human history, but short compared to the development of technological capability. If it takes a species several 100,000 years to develop from basic tool use to spacefaring technology capable of deflecting asteroids or surviving volcanic winters, then most technological civilizations would likely be eliminated before reaching that level of capability. The geological record suggests that Earth has experienced numerous catastrophic events beyond the 5 major mass extinctions. smaller-scale extinction events, regional volcanic catastrophes, and climate disruptions occur much more frequently and could be equally devastating to technological civilizations, even if they don't cause global mass extinctions. The Toba supervolcanic eruption, which occurred approximately 74,000 years ago, provides an example of how even relatively recent catastrophic events can come close to eliminating technological species. The Toba eruption was much smaller than the Siberian Traps volcanism that caused the end Permian extinction, but it still created a volcanic winter that may have reduced the global human population to as few as 10,000 individuals. If early human civilization had been more advanced at the time of the Toba eruption, with cities, agriculture, and complex technology, it's entirely possible that all traces of that civilization would have been erased by the volcanic ash and climate disruption that followed the eruption. Future archaeologists might find no evidence that humans had ever developed beyond hunter-gatherer societies, even if they had actually achieved much higher levels of technological sophistication. This raises the disturbing possibility that mass extinction events might have repeatedly reset not just biological evolution, but also cultural and technological evolution on Earth. Civilizations might have risen and fallen multiple times throughout Earth's history, with each major catastrophic event erasing virtually all evidence of previous technological achievements and forcing intelligence to begin again from scratch. The speed with which catastrophic events can alter Earth's environment also means that there might be very little advance warning before traces of technological civilization are erased. The environmental changes that accompany major asteroid impacts and supervolcanic eruptions happen faster than most geological processes, meaning that the burial and preservation of artifacts would have to occur within the immediate aftermath of the catastrophic event itself. This creates a paradox for the preservation of evidence. The same catastrophic events that are most likely to eliminate technological civilizations are also the events that are most likely to rapidly bury and preserve artifacts from those civilizations. But the environmental conditions during these events are also the most hostile to the survival of artificial materials and structures. The net effect is that mass extinction events represent both the greatest threat to the survival of technological civilizations and the greatest opportunity for the preservation of evidence from destroyed civilizations. Understanding this paradox is crucial for developing strategies to search for traces of ancient intelligence in the geological record. Perhaps most soberly, the frequency and severity of mass extinction events in Earth's past remind us that our own technological civilization exists during what may be a temporary lull between catastrophes. The last major extinction event was 66 million years ago, and the last supervolcanic eruption was 74,000 years ago. In geological terms, we may be overdue for the next planetary reset. This realization adds urgency to both the search for evidence of past civilizations and the development of technologies that might allow our own civilization to survive the next catastrophic event. If previous technological species have indeed risen and fallen throughout Earth's history, then we have the opportunity to learn from their fate and perhaps avoid repeating it. But only if we can find and interpret the faint traces they may have left behind in the geological record. If we are to find evidence of ancient technological civilizations in Earth's geological record, we must learn to think like forensic scientists working a case where the crime scene has been contaminated by millions of years of natural processes. The traditional artifacts that archaeologists seek, tools and pottery and buildings, are unlikely to survive the enormous timescales we're considering. Instead, we must look for more subtle traces, chemical fingerprints, and isotopic signatures that might persist long after all physical structures have crumbled to dust. The concept of technofossils provides a framework for understanding what kinds of traces industrial civilizations might leave in the geological record. Unlike biological fossils, which preserve the physical remains of once living organisms, Technofossils represent the chemical and physical signatures of technological processes embedded in sedimentary layers. These signatures might include unusual concentrations of metals, synthetic compounds that don't occur in nature, or isotopic ratios that can only be produced by industrial processes. Our own industrial civilization is currently creating a massive technofossil record that future geologists will be able to detect for millions of years to come. The carbon dioxide we've released by burning fossil fuels has altered the isotopic composition of the atmosphere and oceans in ways that will be preserved in sedimentary rocks forming today. The plastics we've produced are creating microscopic particles that are being incorporated into marine sediments around the world. The nuclear weapons we've detonated have scattered artificial isotopes that will remain detectable for thousands of years. Understanding the modern technofossil record provides crucial insights into what we might expect to find from much older technological civilizations. But it also reveals how challenging the search is likely to be, because many of the most obvious signatures of industrial activity are also the most vulnerable to long-term degradation and alteration. Consider the carbon isotope signature that our civilization is creating through the burning of fossil fuels. Coal, oil, and natural gas are derived from ancient organic matter that was depleted in the heavier carbon-13 isotope relative to the lighter carbon-12 isotope. When we burn these fuels, we're releasing carbon dioxide with a distinctive isotopic signature that's measurably different from carbon dioxide produced by natural processes. This isotopic shift is already being recorded in tree rings, ice cores, and marine sediments around the world. Future scientists examining sedimentary rocks that formed during the 20th and 21st centuries will be able to identify a clear spike in carbon-12 rich carbon dioxide that coincides with the rapid expansion of human industrial activity. The signature is so distinctive that it would be virtually impossible to mistake for any known natural process. But this carbon isotope signature also illustrates the challenges of detecting ancient technofossils. The excess carbon dioxide we're releasing will eventually be absorbed by the oceans and incorporated into marine sediments. But over time, the distinctive isotopic signature will be diluted and modified by natural carbon cycling processes. After a few million years, the spike might still be detectable, but it would require sophisticated analytical techniques and careful sampling to distinguish it from natural variations in the carbon cycle. The problem becomes even more challenging when we consider that any ancient civilization might have used completely different energy sources than fossil fuels. A civilization that developed fusion power or solar energy might leave no carbon isotope signature at all. A civilization that burned biomass rather than fossil fuels might create isotopic changes that would be indistinguishable from natural forest fires or volcanic emissions. This uncertainty about energy sources highlights the importance of looking for multiple independent signatures of industrial activity rather than relying on any single type of evidence. A genuine technofossil layer should show a cluster of anomalies that all point toward artificial rather than natural processes, creating a cumulative case that's stronger than any individual piece of evidence. Metal concentrations provide another category of potential technofossils that might be more durable than organic signatures. Industrial civilizations typically concentrate and redistribute metals in ways that are very different from natural geological processes. Mining operations extract metals from dispersed ore deposits and concentrate them in specific locations. Smelting and manufacturing processes can create metal alloys and compounds that don't occur naturally. Waste disposal can create unusual accumulations of toxic metals in sedimentary environments. Our own civilization is creating distinctive metal signatures that will persist in the geological record for much longer than our carbon emissions. Lead pollution from gasoline additives has created a global spike in lead concentrations in sediments that began in the early 20th century and peaked in the 1970s. This lead spike is so pronounced and geographically widespread that it will serve as a clear marker of industrial activity for millions of years to come. Similarly, platinum group elements from automobile catalytic converters are creating unusual accumulations along highways and in urban sediments. These elements are extremely rare in crustal rocks, but are being concentrated and dispersed by human activities in patterns that would be impossible to produce naturally. The signature is subtle, but persistent, and could potentially be detected in ancient sedimentary layers if similar processes had operated in the past. But metal signatures also have limitations as technofossil markers. Natural geological processes can also concentrate metals in unusual ways through hydrothermal activity, metamorphism, or weathering of unusual rock types. Distinguishing artificial from natural metal anomalies requires understanding the full range of processes that can affect metal distributions over geological time. Synthetic compounds represent perhaps the most unambiguous category of potential technofossils. These are molecules that don't exist in nature and can only be produced through deliberate chemical synthesis. Our civilization has created thousands of such compounds, from plastics and pharmaceuticals to pesticides and industrial chemicals. Many of these compounds are designed to be resistant to degradation, and some may persist in the environment for thousands or even millions of years. Polychlorinated biphenyls, or PCBs, provide an example of synthetic compounds that could serve as long-term technofossil markers. These chemicals were widely used in electrical equipment and industrial applications from the 1930s to the 1970s. They're extremely stable and resistant to degradation, and have accumulated in sediments around the world. Even though PCB production was banned decades ago, these compounds will remain detectable in sedimentary layers for potentially millions of years. But synthetic compounds also face significant challenges for long-term preservation. Most organic molecules are thermodynamically unstable at Earth's surface and will eventually be broken down by heat, pressure, radiation, or biological activity. The timescales for this degradation vary enormously depending on the specific compound and environmental conditions, but few organic molecules are likely to survive intact for tens of millions of years. However, even when the original synthetic compounds are destroyed, they may leave behind distinctive breakdown products or elemental signatures that could still be recognized as artificial in origin. Chlorinated compounds, for example, might leave behind unusual chlorine isotope ratios that don't match natural processes. Fluorinated compounds might create distinctive fluorine signatures in sedimentary layers. Nuclear materials represent a special category of technofossils because their decay rates are completely independent of environmental conditions. The artificial isotopes produced by nuclear reactors and weapons will continue to decay according to their fixed half-lives, regardless of temperature, pressure, or chemical conditions. Some of these isotopes, like plutonium-239, with its 24,000-year half-life, will remain detectable for hundreds of thousands of years. The nuclear signature of our civilization is already being recorded in sedimentary layers around the world. Fallout from atmospheric nuclear weapons testing in the 1950s and 60s created a global spike in radioactive isotopes that marks the beginning of what some scientists call the Anthropocene epoch. This nuclear signature is so distinctive and widespread that it will serve as a chronological marker in the geological record for hundreds of thousands of years. But nuclear signatures also have limitations as evidence for ancient civilizations. The isotopes with the longest half-lives are also the ones that are produced in the smallest quantities, making them difficult to detect after extended periods. Moreover, we can't assume that ancient civilizations would have necessarily developed nuclear technology, or that they would have used it in ways that would create detectable signatures in the geological record. Perhaps most challenging of all is the question of how to distinguish ancient technofossil signatures from the background noise of natural geological processes. The Earth's crust contains trace amounts of virtually every element in the periodic table. distributed through complex interactions between igneous, sedimentary, and metamorphic processes. Natural variations in elemental concentrations and isotopic ratios can be enormous, potentially masking subtle artificial signatures. This problem is compounded by the fact that we don't yet fully understand all the natural processes that can affect the distribution of elements and isotopes in sedimentary rocks. New discoveries in geochemistry regularly reveal previously unknown mechanisms for concentrating or fractionating elements, processes that might have been mistakenly interpreted as artificial if they had been discovered in the context of searching for ancient technofossils. The key to overcoming these challenges lies in developing increasingly sophisticated analytical techniques and building comprehensive databases of natural geochemical variations. Modern mass spectrometry can detect elemental concentrations at the parts per billion level and measure isotopic ratios with extraordinary precision. These capabilities are constantly improving, allowing scientists to detect fainter and fainter signals against increasingly well-characterized natural backgrounds. Statistical analysis also plays a crucial role in distinguishing artificial from natural signatures. Natural processes typically produce characteristic patterns of variation that can be modeled and predicted. Artificial processes should produce signatures that fall outside the range of natural variation, or that show patterns of correlation that can't be explained by known geological processes. But statistical approaches require large data sets and careful sampling strategies to be effective. A single anomalous measurement is rarely sufficient to establish artificial origin, especially when dealing with samples that are millions of years old and may have been altered by subsequent geological processes. Building convincing cases for ancient technofossils will require systematic surveys of multiple sites, multiple analytical techniques, and multiple independent lines of evidence. The search for ancient technofossils is further complicated by the fact that we don't know what kinds of technologies ancient civilizations might have developed. Our search strategies are inevitably biased toward detecting the kinds of signatures that our own civilization produces, but there's no guarantee that ancient civilizations would have followed similar technological pathways. A civilization that developed primarily biological technologies, for example, might leave entirely different signatures than one based on metallurgy and chemistry. A civilization that achieved sustainability and operated within natural cycles might leave much subtler traces than one that relied on extractive industries and waste disposal. A civilization that existed for only a brief period might leave barely detectable signatures, while one that operated for millions of years might create cumulative effects that are easier to identify. Despite these challenges, the search for technofossils in ancient rocks is not hopeless. The analytical capabilities of modern geochemistry are extraordinary and continue to improve rapidly. Our understanding of natural geochemical processes is becoming increasingly sophisticated, providing better frameworks for recognizing genuine anomalies. And the stakes are high enough to justify intensive investigation, because finding evidence of ancient civilizations would fundamentally change our understanding of intelligence and technology in the universe. The current efforts to identify technofossils in the geological record are still in their early stages, but they're already yielding interesting results. Several research groups are systematically analyzing sedimentary sequences for unusual elemental concentrations, isotopic anomalies, and synthetic compounds. While no definitive evidence for ancient industrial activity has yet been found, the search is revealing new insights into natural geochemical processes and pushing the boundaries of analytical chemistry. Perhaps most importantly, the development of technofossil search strategies is providing a new perspective on our own industrial civilization and its long-term impact on the planet. By learning to read the signatures that we're currently writing in the geological record, we're gaining a deeper appreciation for how technological civilizations interact with planetary systems, and what kinds of traces they're likely to leave for future discovery. The rocks beneath our feet are more than just geological formations. They're libraries containing 4.5 billion years of Earth history, including potentially the history of intelligence and technology on our planet. Learning to read these libraries will require new techniques, new collaborations between different scientific disciplines, and new ways of thinking about the relationship between civilization and the geological record. But the potential rewards, both scientific and philosophical, make the effort worthwhile. To understand how evidence of ancient civilizations might be preserved or destroyed on Earth, we must look beyond our own planet to the laboratory of the solar system. Mars and Venus, our nearest planetary neighbors, offer crucial insights into how planetary histories unfold and what happens to surface features over geological time. These worlds have experienced dramatically different evolutionary paths, providing natural experiments in planetary preservation and erasure that inform our search for traces of ancient intelligence on Earth. Mars presents perhaps the most sobering example of how planetary processes can erase evidence of complex surface features over time. The red planet today appears desolate and lifeless, its thin atmosphere and frigid temperatures hostile to any form of complex organization. But billions of years ago, Mars was a very different world, with a thicker atmosphere, liquid water on its surface, and conditions that might have been suitable for life and perhaps even intelligence. The evidence for ancient Mars's more hospitable past is written across its surface in the form of dried riverbeds, ancient lake beds, and massive flood channels that dwarf anything on Earth. The Valles Marineris canyon system stretches over 4,000 kilometers across the Martian surface, a geological feature so vast that it would span the entire width of the United States. Countless smaller valleys and channels snake across the ancient highlands, testimony to a time when water flowed freely across the Martian landscape. But this evidence of past habitability comes with a sobering lesson about the fragility of planetary environments. The processes that transformed Mars from a potentially habitable world to the frozen desert we see today operated over hundreds of millions of years, gradually stripping away the atmosphere and desiccating the surface. If Mars had harbored complex life, or even technological civilizations during its more hospitable past, virtually all traces of such activity would have been erased by the planetary transformation that followed. The Martian atmosphere provides a particularly stark example of how planetary conditions can change over geological time. Mars today has an atmospheric pressure less than 1% of Earth's, far too thin to support liquid water at the surface. But geological evidence suggests that early Mars had a much thicker atmosphere, possibly dense enough to maintain surface temperatures above the freezing point of water for extended periods. The loss of this atmosphere appears to have been driven by several factors working in combination. Mars's small size means it has a weaker gravitational field than Earth, making it easier for atmospheric gases to escape to space. The planet's lack of a strong magnetic field provides little protection from the solar wind, which can strip away atmospheric particles over time. Volcanic activity, which replenishes atmospheric gases on Earth, appears to have ceased on Mars billions of years ago, cutting off the supply of new gases to replace those lost to space. The implications for the preservation of evidence are profound. Any structures or artifacts left on the Martian surface billions of years ago would have been subjected to temperature swings from potentially habitable conditions to the current extreme cold. Atmospheric pressure changes from Earth-like densities to near vacuum conditions, and radiation exposure that increased dramatically as the protective atmosphere was stripped away. Even more destructively, the changing atmospheric conditions would have driven massive dust storms and erosional processes that could have buried or scoured away surface features. The dust storms on Mars today can engulf the entire planet for months at a time, moving enormous quantities of fine particles across the surface. Over millions of years, such processes could easily erase all traces of artificial structures, no matter how well built they might have been originally. Venus presents an even more extreme example of planetary transformation and surface erasure. Hidden beneath its dense carbon dioxide atmosphere and sulfuric acid clouds, Venus harbors surface temperatures of over 460 degrees Celsius, hot enough to melt lead and far beyond the survival limits of any known materials. The atmospheric pressure at the surface is over 90 times that of Earth, equivalent to the pressure found nearly a kilometer underwater in Earth's oceans. But like Mars, Venus may not always have been so hostile. Some models suggest that early Venus might have had liquid water oceans and relatively moderate surface temperatures for the first billion years of its existence. If so, Venus would have been potentially habitable during the same time period when life was first emerging on Earth. The transformation of Venus from a potentially habitable world to the hellish greenhouse it is today appears to have been driven by a runaway greenhouse effect. As the sun gradually increased in brightness over geological time, more water evaporated from Venus's oceans. Water vapor is a potent greenhouse gas, trapping more heat and causing even more water to evaporate in a positive feedback loop that eventually boiled away the entire ocean. The water vapor in the upper atmosphere was then broken apart by solar radiation, with the hydrogen escaping to space and the oxygen combining with surface rocks. What remained was a dense carbon dioxide atmosphere that trapped heat so efficiently that surface temperatures soared to their current extreme levels. The surface of Venus today shows evidence of relatively recent geological activity, with volcanic features and impact craters that suggest the planet has been geologically resurfaced within the last few 100 million years. This resurfacing would have completely erased any evidence of earlier surface features, including any hypothetical traces of ancient life or civilization that might have existed during Venus's more temperate past. The lesson from Venus is that even planets that remain geologically active can experience such dramatic environmental changes that all evidence of earlier conditions is completely erased. The combination of extreme temperatures, corrosive atmospheric chemistry, and geological resurfacing would destroy any conceivable artifacts or structures, leaving no trace of previous inhabitants, even if they had once existed. But the study of Mars and Venus also provides insights into how we might detect evidence of ancient civilizations on other worlds. Insights that can be applied to the search for such evidence on Earth. Remote sensing techniques developed for planetary exploration have revealed subtle signatures of past environmental conditions that would have been impossible to detect from ground-based observations alone. Spectroscopic analysis of the Martian surface has revealed the presence of minerals that can only form in the presence of liquid water, providing evidence for past habitability that persists long after the water itself has disappeared. Similarly, analysis of the Venus atmosphere has revealed isotopic ratios that tell the story of atmospheric evolution and water loss over billions of years. These same techniques, when applied to Earth's geological record, might reveal signatures of past technological activity that would be impossible to detect through conventional archaeological methods. Spectroscopic analysis of ancient sedimentary rocks could potentially identify unusual mineral assemblages or chemical compositions that indicate artificial processing. Isotopic analysis could reveal signatures of industrial activity that persist long after all physical artifacts have been destroyed. The search for life on Mars has also driven the development of increasingly sophisticated techniques for detecting biological signatures in ancient rocks. The same analytical methods that are being developed to search for fossil microbes in Martian meteorites could potentially be adapted to search for technological signatures in Earth's geological record. Perhaps most importantly, the study of planetary evolution has revealed how dynamic and unpredictable planetary environments can be over geological time. The transformation of Mars from a potentially habitable world to a frozen desert, and Venus from a possible ocean world to a hellish greenhouse, demonstrates that planetary conditions that seem stable on human timescales can change dramatically over millions or billions of years. This dynamic nature of planetary environments has profound implications for the survival of technological civilizations and the preservation of evidence from such civilizations. A civilization that develops during a geologically and climatically stable period might thrive for thousands or millions of years, only to be eliminated by planetary changes that occur on much longer timescales. The concept of planetary habitability zones provides another perspective on how technological civilizations might be affected by long-term environmental change. The habitable zone around a star is the range of distances where liquid water can exist on a planet's surface. But this zone is not static. As stars evolve and change in brightness, the habitable zone moves inward or outward, potentially leaving previously habitable worlds frozen or scorched. Our own sun is gradually increasing in brightness as it ages and will eventually become hot enough to boil away Earth's oceans in a runaway greenhouse effect similar to what appears to have happened on Venus. This solar evolution operates on timescales of billions of years, much longer than the existence of complex life on Earth. But it demonstrates that even the most stable planetary environments are ultimately temporary. The study of exoplanets, worlds orbiting other stars, is providing an even broader perspective on how planetary systems evolve and what kinds of conditions might be suitable for the development and preservation of technological civilizations. Thousands of exoplanets have now been discovered, revealing an extraordinary diversity of planetary types and orbital configurations that were never imagined before the era of exoplanet detection. Some exoplanets orbit very close to their stars, with surface temperatures hot enough to vaporize rock. Others orbit so far away that any atmosphere would be frozen solid. Some planets have highly elliptical orbits that cause extreme seasonal variations in temperature and radiation. Others are tidally locked to their stars, with one side permanently facing the star and the other permanently dark. This diversity of exoplanetary environments suggests that the relatively stable conditions that have allowed complex life to evolve on Earth may be quite rare in the universe. Most planetary environments appear to be subject to extreme variations in temperature, radiation, or atmospheric chemistry that would make the development of technological civilizations very difficult. But exoplanet research is also revealing potential signatures of technological activity that might be detectable across interstellar distances. The analysis of exoplanet atmospheres through spectroscopy could potentially reveal artificial atmospheric compositions that indicate industrial activity. Large-scale engineering projects, like the construction of solar collectors or habitat structures, might be detectable through their effects on the light curves of distant stars. These techniques for detecting technological signatures on exoplanets provide models for what we might look for in Earth's own geological and atmospheric record. If industrial civilizations can produce detectable signatures in the atmospheres of distant worlds, then similar signatures might be preserved in the atmospheric compositions recorded in ancient ice cores or sedimentary rocks on Earth. The search for technological signatures on exoplanets is still in its early stages, but it's already pushing the boundaries of what kinds of evidence we might accept as indicators of technological activity. This work is forcing scientists to think creatively about what technological civilizations might look like and what kinds of traces they might leave in their planetary environments. Perhaps most importantly, the study of other worlds is providing a broader context for understanding Earth's own geological and atmospheric evolution. By comparing Earth to Mars and Venus, and to the growing catalogue of exoplanets, we can better appreciate both the remarkable stability that has characterized our planet's environment and the potential for dramatic changes that might occur in the future. This comparative planetary perspective also helps calibrate our expectations for finding evidence of ancient civilizations on Earth. If Mars and Venus have experienced such dramatic environmental changes that all evidence of past surface conditions has been erased or heavily modified, then we should expect that Earth's geological record might also be missing crucial information about past environmental conditions and potential past inhabitants. But the same techniques that are revealing the hidden histories of Mars and Venus, and that are beginning to probe the atmospheric compositions of distant exoplanets, might also be capable of uncovering evidence of ancient technological activity on Earth. The challenge is learning to read the subtle signatures that might persist in our planet's geological and atmospheric records, signatures that could tell us whether we are truly alone in the history of intelligence on Earth. The laboratory of the solar system continues to reveal new insights into how planetary environments evolve and what kinds of traces different types of activity might leave in the geological record. As our techniques for analyzing planetary surfaces and atmospheres continue to improve, we may find that the search for ancient civilizations on Earth benefits as much from looking outward to other worlds as from looking downward into our own planet's geological past. Throughout human history, cultures around the world have preserved stories of great floods, lost civilizations, and golden ages that existed before recorded history began. These myths and legends, passed down through countless generations of oral tradition, have often been dismissed by modern scholars as pure fantasy, creative explanations for natural phenomena that ancient peoples could not understand scientifically. But a growing body of research suggests that some of these stories might contain kernels of genuine historical memory, preserving information about real events that occurred thousands or even tens of thousands of years ago. The most widespread and persistent of these ancient stories are flood myths, found in virtually every culture that has left written or oral records. From the biblical account of Noah's Ark to the Mesopotamian epic of Gilgamesh, from Hindu stories of Manu and the Great Deluge to Native American traditions of world-destroying floods, these narratives share remarkably similar elements despite arising in geographically separated cultures that had no contact with each other. The traditional academic explanation for this universality has been that flood stories represent a common human response to the local flooding that affects all agricultural societies. Rivers overflow their banks, coastal areas are inundated by storms, and these traumatic events naturally become incorporated into cultural narratives about divine punishment and renewal. The similarities between flood myths from different cultures, according to this view, reflect the universal human experience of water as both a life-giving and life-destroying force. But recent research in geology and archaeology is revealing that some flood myths might actually preserve memories of specific catastrophic events that had genuine global or regional impacts. The most compelling evidence comes from the Black Sea, where geological investigations have uncovered evidence for a massive flooding event that occurred approximately 7,600 years ago. The Black Sea deluge hypothesis, developed by marine geologists William Ryan and Walter Pittman, suggests that the Black Sea was originally a much smaller freshwater lake, isolated from the Mediterranean by a natural dam at what is now the Bosphorus Strait. As sea levels rose following the end of the last ice age, Mediterranean waters eventually breached this natural barrier, causing salt water to pour into the Black Sea basin at a rate that dwarfed any modern waterfall. The flooding would have been catastrophic for any human settlements around the original lakeshore. Archaeological evidence suggests that the region was indeed inhabited by early agricultural communities at the time of the proposed flood. These communities would have been forced to flee as the rapidly rising waters submerged their homes, fields, and entire way of life. The scale and speed of this flooding event would have created exactly the kind of traumatic collective memory that could be preserved in oral tradition for thousands of years. The survivors would have carried stories of the Great Flood with them as they disperse to new regions, spreading the narrative across the developing civilizations of Europe, Asia, and the Middle East. Supporting evidence for this interpretation comes from linguistic analysis of flood myths, which shows patterns of diffusion that match the expected migration routes of Black Sea refugees. The oldest versions of flood stories appear in the Middle East and gradually spread outward, becoming more elaborate and mythologized with each retelling, but retaining core elements that point back to a common source event. The Black Sea deluge is not the only geological event that might be preserved in human cultural memory. The Lachaussee eruption in Germany, which occurred approximately 12,900 years ago, was one of the largest volcanic eruptions in European history. The eruption would have had devastating effects on human populations across much of Central and Northern Europe, and may be preserved in Germanic and Celtic traditions of fires from the sky and the destruction of the old world. Even more intriguingly, some researchers have suggested that Aboriginal Australian oral traditions preserve memories of events that occurred during the last ice age, when sea levels were much lower than today and Australia was connected to New Guinea by a land bridge. Stories describing the flooding of coastal areas and the isolation of islands match remarkably well with the geological history of sea level rise over the past 20,000 years. The preservation of such ancient memories in oral tradition might seem impossible given the timescales involved, but ethnographic research has revealed that some cultures maintain oral histories with remarkable accuracy over periods of centuries or even millennia. Aboriginal Australian cultures, in particular, have demonstrated the ability to preserve detailed geographical and astronomical information in their song cycles and storytelling traditions for periods that extend well beyond the reach of written history. This research into the geological basis of flood myths and other ancient traditions provides a valuable perspective on how we might approach the search for cultural memories of much older events. If human oral tradition can preserve accurate information about events that occurred thousands of years ago, then it's conceivable that some myths and legends might contain echoes of even more ancient occurrences, perhaps including encounters with technological civilizations that predated our own. But this possibility must be approached with extreme caution, because the same psychological and cultural processes that can preserve genuine historical memories can also create completely fictional narratives that have no basis in actual events. The human mind has a powerful tendency to create meaningful stories out of random or disconnected information, and cultural transmission can transform minor events into epic narratives over the course of many retellings. The key to distinguishing genuine historical memories from pure mythology lies in comparing mythological narratives with independent geological and archaeological evidence. When flood myths align with specific geological events that can be dated and characterized through scientific methods, we have reason to take the stories seriously as potential historical records. When mythological narratives have no corresponding evidence in the physical record, they're more likely to represent purely symbolic or religious concepts rather than historical memories. This approach has been successfully applied to several categories of ancient traditions beyond flood myths. Stories of volcanic eruptions, earthquakes, and meteor impacts from various cultures have been correlated with specific geological events, demonstrating that oral tradition can indeed preserve accurate information about natural disasters over extended periods. But applying this methodology to search for memories of ancient civilizations presents unique challenges. Unlike natural disasters, which leave clear physical evidence in the geological record, the traces of ancient technological civilizations might be so subtle or degraded that they're difficult to distinguish from natural phenomena. Moreover, stories about lost civilizations are particularly prone to embellishment and mythologization because they often serve important cultural functions related to identity, origin, and destiny. Consider the widespread traditions of golden ages and lost wisdom that appear in cultures around the world. Hindu cosmology describes cycles of creation and destruction spanning millions of years, with advanced civilizations rising and falling in endless repetition. Greek mythology tells of a golden age when humans lived in harmony with the gods, followed by progressively more degenerate ages, culminating in the current Iron Age. Similar themes appear in Mesoamerican traditions, Norse mythology, and countless other cultural contexts. These stories might represent genuine cultural memories of more advanced prehistoric societies, but they could equally well represent universal human nostalgia for an imagined better past, or symbolic representations of spiritual and moral concepts that have nothing to do with actual historical events. The ubiquity of Golden Age myths might reflect the common human experience of technological and social change, with each generation remembering the previous era as simpler and more harmonious than the present. The challenge becomes even more complex when we consider that some traditions explicitly describe technological capabilities that seem anachronistic for their supposed time periods. Ancient Indian texts describe flying vehicles called vimanas, complete with detailed technical specifications for their construction and operation. Sumerian texts refer to the Anunnaki, beings who supposedly possessed advanced technology and knowledge. Various cultures describe mysterious teachers or civilizers who brought knowledge of agriculture, writing, and other technologies from unknown sources. These technological anachronisms in ancient texts have been seized upon by proponents of ancient astronaut theories and lost civilization hypotheses as evidence for prehistoric advanced societies or extraterrestrial contact. But mainstream scholarship generally interprets these descriptions as mythological or symbolic, rather than literal accounts of actual technology. The problem is that distinguishing between literal and symbolic interpretations of ancient texts requires a deep understanding of the cultural and linguistic contexts in which the texts were created. Modern readers, approaching ancient texts with contemporary assumptions about the relationship between language and reality, may misinterpret metaphorical or spiritual descriptions as literal technical information. Moreover, the process of translation and transmission over thousands of years can dramatically alter the meaning and content of ancient texts. Words and concepts that had specific meanings in ancient languages may have no direct equivalents in modern languages, leading to translations that impose contemporary interpretations on ancient ideas. Despite these challenges, some researchers have attempted to identify patterns in ancient traditions that might point toward genuine memories of advanced prehistoric civilizations. They note that stories of lost civilizations often include specific details about technological capabilities, geographical locations, and historical sequences that might be too complex and consistent to have been invented independently by different cultures. The Atlantis story, as recorded by Plato in his dialogues Timaeus and Critias, provides perhaps the most famous example of such detailed descriptions. Plato describes a technologically advanced maritime civilization that existed 9,000 years before his own time, located beyond the Pillars of Hercules in the Atlantic Ocean. The civilization is described as having sophisticated engineering capabilities, a complex political system, and military technology that allowed it to threaten the ancient Mediterranean world. The specificity and internal consistency of Plato's account have led some researchers to suggest that it might be based on